So in our last lecture, we studied all about the circular motion. So let us take a quick review, okay, before starting the rotational motion. So consider a circle, and on this circle, consider there is some object. This green color point is an object. Now, if this object moves in a circle with a constant velocity v, then what does this mean? This means that the object, it means, say, first of all, if something moves with a constant velocity, there is no force. So as I said, this object is moving with a constant velocity along the circumference of the circle. So is there any linear force? No. So I can write force linear equals to 0. Agreed. Now, as I said, to keep the object on the circumference of the circle, we need a force, and that force always acts towards the center, that we have already discussed in detail in our last class. So if there is an object moving at a constant velocity along a circle, then the force required to keep this object on the circle is called centripetal force, and it is equals to m v square. V is the velocity with which it is moving, and r is the radius of the circle on which it is moving. Agreed? So remember, the linear force is 0 here because the object is moving at a constant velocity. So even if the object is moving at a constant velocity, there is always a centripetal force. The reason for the existence of centripetal force, because this force is required to keep the object in circular motion, as we have already discussed in our last class. In this lecture, we are not concerned with this actually. In rotation, we are least concerned with the centripetal force. The reason is, now we will be dealing with objects which are rigid. In this chapter, we will be dealing with objects which are rigid. So consider this is a rod, okay, and consider this rod, say an iron rod, is fixed here. So there is a point here on which one end of the rod is fixed. Now if you apply a force, say you apply a force here, agreed, then what happens? You all know that this object is going to move in a circle. That is sure. Agreed? So if this is the, so if let r is the length of the rod and you give a force F, agreed, then this force F causes the rod to move on a circle. Now let me tell you something interesting. Now consider the same rod, okay, and instead of applying the force here, you don't apply the force here. Now consider you apply the force somewhere around here. Agreed? Now no doubt, again the rod will move in a circular motion, tracing out a circle. But can you tell me one thing? If you apply a force at this position, say this position is at a distance r dash from the center, okay, and if you apply a force F on the edge of the rod, can you tell me which one is easier for you to make the rod move? For example, you might have seen in your day-to-day life, you open the door. So consider if this is a door, then you always see you open the door by using your hands on here. So you push the door at its edge because it is easy to push. But you try opening a door by applying force somewhere near the hinge joint. Okay, so consider this is your door, okay, and this is a joint. You always apply a force on the edge of the door to open it. Therefore you have a knob at the edge of the door, because with less force you can open the door. But try once putting the same force here and pushing the door will hardly move. This gives us an interesting conclusion. In case of rigid object, force is not the only thing that is important, because force is not deciding the motion. Apart from force, there is one more place, that one more thing that decides the motion is where you are applying the force. Agreed? So these two things together is necessary to understand rotational motion, because both these factors are responsible for motion in case of rotation. See, in linear translational motion, so if you have objects moving along one dimension, only force was the deciding factor. You have an object, you apply the force. The more the force is, the more is the motion. So if you increase the force, what happened? Acceleration increases. By acceleration, I mean the amount of motion, because acceleration is a measure of amount of motion. So if you increase the force, then logical thing was that the amount of motion in the ball was increasing. But in rigid objects, which has the power to move around a circle, just by increasing the force, you cannot say that you are going to create some good circular motion. There is one more thing that also has to be taken into consideration, is where you are applying the force. If you are applying the force at a larger distance, then the motion is going to be fast. If you apply the force somewhere around here at a smaller distance, then it is very difficult to push this rod around the circle, and not only that, but it will not move with that speed. Hence we were bound to define a new quantity in rotational motion, that is torque. And this torque tau is represented as a multiplication of r and f. So why did we multiply r and f? Because in rotational motion, both r and f, both f and r, they were both deciding the motion. The motion is not single-handedly decided by force, but also where you are applying the force. That's why we were bound to define a new term called as the torque. So now you can say the more is the torque, the more is the rotational effect that can be seen on rigid object. Let me repeat. In rotational motion, the analog of this torque, so in one dimension motion, so what was the main thing that decided motion? The only thing that decided motion was force in one dimensional motion. But in rotational motion, the main thing that decided motion is torque, and torque is a multiplication of r and f, because both these things, they decide the net effect. Again, both these things, they decide the net effect. So what do we say? So we say the more the torque is, the better is the rotational effect. Hence, in rotation, instead of force, we read about torque, because torque is the deciding factor. Agreed? Now, in the next lecture, now we'll talk more on rotational motion.